Hello, and welcome to Sleep Gravity. In this quiet moment, as the light around you has softened, and the sounds outside slowly fade into the distance, imagine that far from Earth, there is a small world moving around its star in an orbit almost impossibly tight. It does not drift slowly through the cold darkness like the distant planets. It does not rest at a safe distance, where rock can cool and an atmosphere can wrap around the surface for billions of years. This world is flying very close to the light of its parent star, so close that each orbit is like passing through fire. On the side facing the star, the rocky surface is heated intensely. Red, orange cracks open across the dark crust. Mineral vapor rises from the ground, then is pulled behind into a long trail of dust, gently curved through space, like the tail of a comet. But this is not an icy comet melting near the sundae. This may be a rocky planet, a world that once had a shape of its own, slowly losing itself in the overwhelming light of its star. What is strange is that this disappearance does not happen like a great explosion. There is no single moment that marks the end. There is no image of a planet bursting apart in silence and dissolving into the dark. Instead, the process may unfold little by little with each orbit. A very thin layer of material is heated, some gas or dust escapes the planet's weak gravity, and then starlight and stellar wind stretch it outward into a faint tail. From far away, we do not see this planet the way we see the moon in the sky. We do not have a sharp image showing every stone, every crack, or every cloud of dust rising from its surface. Most of what we know comes from the light of the star behind it. When the planet passes in front of its host star, that light dims slightly. If the planet were a normal round body, the shadow it left behind would also follow a fairly steady rhythm. But with a world that is coming apart, the shadow is no longer neat. It stretches, changes, sometimes deeper, sometimes shallower, as if an unstable veil of dust is drifting with the planet through each orbit. It is from these tiny changes that telescopes began to recognize a quiet story taking place. A planet may be having pieces of itself stripped away by its own star. Rock, which in everyday life makes us think of solidity and endurance, may there become vapor. Minerals can rise like heated smoke, then cool into tiny grains of dust. Those grains pass in front of the starlight, blocking a small fraction of it, and changing the way that light reaches our telescopes. And inside that faint, fragile-looking trail, there may be information about the makeup of a distant rocky world. It may be rich in silicates. It may carry traces of metals. It may contain minerals that once belonged to the crust or to deeper parts of the planet. In other words, as that planet slowly loses material, it also accidentally leaves us a sample made of light. On this journey, we will not look at an evaporating planet as a sensational spectacle, but as a very slow and very distant scientific process where heat, gravity, light, and dust together write the fate of a world. We will move from the small shadow in front of the star to the rocky surface being intensely heated, from the long comet, like dust tail, to the way telescopes read the composition of material grains that are almost impossible to see. And the deeper we go, the clearer the central question will become. What truly happens to a rocky planet when it flies too close to its star? So close that each orbit may take away another piece of its atmosphere, another layer of its surface, and perhaps one very small part of the history that once formed it? Far away, at distances so vast that even stars become little more than points of light within streams of data. The story of this planet did not begin with a clear image. We do not see it as a rocky sphere drifting quietly through space. We do not directly observe the glowing red fractures across its surface, nor do we immediately see the trail of dust stretching behind it. What first reached astronomers was simply the light of a star, a steady flow of brightness that seemed to repeat from one observation to the next. Within that light, there were occasionally tiny dips, so small that in everyday life they might resemble a distant lamp, briefly dimming as a speck of dust passes in front of it. Yet for a telescope, changes that subtle can reveal the presence of an entire world. The discovery of many exoplanets begins with something just that simple. When a planet passes in front of its star, as seen from Earth, it blocks a small portion of the starlight. The effect is not dramatic. For a small planet, the brightness may decrease only slightly before returning to normal once the planet moves away from the stellar disk. If this pattern repeats regularly, scientists can eventually infer that an object is orbiting the star. This technique is known as the transit method, a way of finding planets not by looking directly at them, but by observing the tiny shadow they leave upon starlight. It may sound delicate in principle, but in practice, it has become one of the most important ways humanity has learned that planets exist not only around the Sun, but around countless other stars throughout the galaxy. For a typical planet, that shadow usually follows a fairly predictable pattern. The starlight dims as the planet begins to cross in front of the star, remains slightly reduced for a short time, and then rises again as the planet moves away. When plotted as a light curve, the result resembles a neat dip, rhythmic and relatively consistent from one orbit to the next. From the depth of that dip, scientists can estimate the planet's size. From the interval between repeated dimmings, they can determine how long the planet takes to complete an orbit. From the duration of the transit itself, they gain additional clues about the planet's path around its star. Each small detail hidden within the light, if measured precisely enough, can become part of a sketch of a world no human eye has ever seen. But some shadows do not behave that way. They are not regular, not tidy, and not perfectly repeatable. Sometimes the starlight dims more deeply, and sometimes less. Occasionally the fading lasts longer than expected, as though the object crossing the star is not simply a round planet, but something carrying an extension behind it. The light curve no longer resembles the clear footprint of a solitary sphere. Instead, it looks more like a soft sweep, an unstable veil drifting across the face of the star. It is this unusual behavior that makes the story so intriguing. If a solid planet blocks light only according to its size, then what is creating this elongated, changing pattern? Why would the shadow of a world begin to resemble the shadow of a cloud of dust? One possibility gradually emerged. The planet may no longer be preserving the clean shape of a simple rocky sphere. It may be losing material. Around it, there could be a cloud of mineral dust, produced as the surface is heated intensely, as rock and minerals vaporize and later condense into tiny particles. These grains do not remain close to the surface. They are carried along the orbit, pushed by starlight, influenced by stellar winds, and eventually drawn into a long, thin, unstable structure trailing behind the planet. When both the planet and this dusty tail pass in front of the starlight is no longer blocked only by a small circular body. It is also dimmed by a broader, longer, and constantly changing stream of dust. As a result, the shadow recorded by telescopes becomes a shadow with a tail. What matters here is not simply that the planet blocks light, it is how the light is blocked. A neat shadow tells us that a stable object is passing by. A distorted, stretched, and changing shadow tells a different story. It suggests that material is leaving the planet, that dust grains are drifting through space, and that a process of gradual loss is unfolding within the star's intense glare. Telescopes cannot hear rock cracking. They cannot feel the heat. They cannot see individual dust grains with the naked eye, but they can measure the tiniest absence of light. And sometimes it is that missing light that carries the richest information of all. A quieter way to imagine this is to picture a still room illuminated by a lamp. If someone walks between you and the light, their shadow briefly crosses the wall and disappears. But if a thin trail of smoke follows behind them, the shadow becomes less distinct. It stretches, softens, and changes with the motion of the smoke. You do not need to see every particle directly to know that something is drifting behind. You only need to observe how the light is being dimmed. In much the same way, telescopes study evaporating planets, only on a vastly larger scale. They watch the light of a star dozens, hundreds, or even thousands of light years away and recognize that a small world is passing in front of it carrying behind it a trail of scattered material, almost like the final breath of stone. From this unusual shadow, the questions begin to grow. If dust truly exists behind the planet, where does it come from? If it originates from the surface, what could heat rock enough to make it vaporize? If the planet is losing material, how long can that process continue? And are we witnessing a rare stage in the life of a rocky world? These questions do not arrive all at once like a sudden noise. They emerge slowly, from a subtle light curve, from an uneven dip, from the delicate differences between the shadow of an ordinary planet and the shadow of a planet leaving part of itself behind. So before we view the dust tail as a spectacular image, we need to begin at its quietest point, a tiny dimming hidden within the data. A star continues shining almost as usual. A planet passes across it in its brief orbit. An unstable haze trails behind, softening the light in a way that a solitary round planet never could. From that observation, astronomers began to realize that some worlds do more than simply orbit their stars. They are being changed by them, orbit after orbit. And as that shadow returns again and again, it draws us closer to a surface growing ever hotter, to rock that may be turning into vapor, and to the deeper story of how a planet can slowly dissolve into the very light of the star that sustains it. To understand why a planet's shadow can appear stretched, as though dust is trailing behind it, we need to shift our attention to the planet's place within its stellar system. A planet does not begin to disintegrate simply because it is rocky, nor does it lose material merely because it is small. What matters far more is its distance from its host star. Some planets orbit far enough away that their surfaces can cool, their atmospheres can survive for long periods, and day and night can pass in a relatively gentle rhythm. But others lie so close to their stars that the very idea of a year becomes almost unrecognizable. Instead of taking hundreds of days to complete an orbit, as Earth does, they may need only a few dozen hours, or even less. Each orbit is not the passage of a season, but more like another journey through an overwhelming field of light, where the surface has little chance to rest. Within our own solar system, we experience our distance from the sun through familiar things. Afternoons are warmer than mornings, summers differ from winters, deserts feel different from icy landscapes. Yet even the hottest places on Earth exist within a far gentler balance than that found on planets orbiting extremely close to their stars. On those worlds, starlight does more than warm the ground. It pours down with relentless intensity, capable of turning the dayside into an ocean of molten rock, or, in more extreme cases, causing portions of the surface itself to vaporize. In everyday life, rock feels solid, heavy, and enduring. We walk on it, build with it, and see mountains as symbols of stability. But in physics, that stability always comes with conditions. If the temperature becomes high enough, if the pressure is right, and if energy continues to flow in without interruption, even rock can no longer maintain its quiet form forever. A planet that orbits too close to its star receives energy in a very different way from Earth. Every square meter of the star-facing side may absorb far more radiation than what more temperate planets experience. If the planet is tidally locked, meaning one side always faces the star while the other remains turned toward darkness, the contrast can become even more extreme. The day side may glow with intense heat, covered by molten rock and mineral vapor, while the night side may be cooler but not necessarily calm enough to create a stable world in any familiar sense. Between these regions, heat and material can be transported by winds, by flows of magma, and by mineral vapor that rises and later condenses. Together, these processes create a planet that is no longer a quiet, rocky sphere, but a system being heated, stirred, and pushed away from equilibrium. What is particularly interesting is that such planets do not need to be large. In fact, many candidate disintegrating planets may be relatively small rocky worlds with modest masses. When a small planet moves extremely close to its host star, it experiences intense heating, while also struggling to hold onto its outer layers. The heated surface produces mineral vapor, and that vapor can rise above the ground. If enough energy is available, and if the planet's gravity is not strong enough to pull everything back, some of that material begins to escape into space. From the outside, the process does not resemble a single volcano erupting from time to time. It is more like an entire region of the planet slowly breathing material outward beneath the glare of its star. As the vapor moves away from the hottest regions, it can cool and condense into tiny dust grains, which are then carried farther along by starlight and stellar winds. At this point, a common misunderstanding can arise. When we say that a planet is evaporating, it is easy to imagine a drop of water disappearing from a hot pan in a matter of seconds. But planets operate on very different timescales. A rocky world does not vanish after a single orbit. Instead, it may lose tiny fractions of itself over countless journeys around its star. During some periods, the loss of material may become stronger. During others, it may weaken. The amount of dust produced can grow thicker or thinner depending on temperature, surface composition, stellar activity, and many other factors. So in this context, evaporation should not be understood as an instant death. It is a profound process of erosion, unfolding over time, as a world remains so close to its energy source that it can no longer fully preserve its outer layers. From Earth, what makes this process especially valuable to study is not only the extreme temperature, but the combination of conditions that occur together. A planet in such a close orbit completes a circuit around its star very quickly, allowing it to transit many times within a relatively short period of observation. That gives telescopes repeated opportunities to capture its signal. If the planet is shedding dust, each transit may look slightly different from the last, providing clues that the material surrounding it is constantly changing. If the star is bright enough and not too distant, scientists can also measure the light at different wavelengths, helping them understand how the dust absorbs and scatters starlight. In this way, a planet orbiting too close to its star becomes both one of nature's most extreme environments and a cosmic laboratory that could never be recreated on Earth. You might imagine such a world as a small stone placed too close to a giant flame, but even that image falls short. The planet is not standing still before its star. It is continually falling around it along its orbit, held in place by gravity while being heated by starlight, stretched by tidal forces, and surrounded by thin streams of material trying to escape. Each orbit is a repetition, but never a perfect one. The surface may change, the amount of dust may fluctuate, and the tail may become thicker or thinner. Within that seemingly regular rhythm, the planet is writing a very slow history using its own substance. This also helps explain why disintegrating planets occupy a fascinating boundary between the familiar and the strange. They are still rocky planets, formed from materials that may not be entirely different from those found on Earth, Venus, or Mercury. Yet their environments go far beyond anything common within our solar system. If Mercury is already the closest planet to the Sun that we know firsthand, these ultra-hot exoplanets may orbit their stars at distances far more extreme than our everyday intuition suggests. There, rock does not simply endure sunlight. It exists within a thermal regime where the boundaries between surface, atmosphere, and dust can begin to blur. Part of the planet no longer remains beneath the ground. It rises, enters space, and eventually reveals itself to us as a faint mark within the light of a distant star. That unusual shadow, a dip in brightness that is uneven and stretched, as though a cloud of dust trails behind the planet, now has its first explanation. To create such a signature, a planet must exist in an environment hot enough that rocky material is no longer entirely solid, while remaining close enough to its star for energy to continually strip away its outer layers. But heat is only one part of the story. Once mineral vapor has risen from the surface, the next crucial question is whether the planet can hold on to that material. Some worlds are extremely hot and still manage to retain portions of an atmosphere, while smaller worlds may allow material to escape much more easily. To understand why part of a planet can truly leave it and enter space, we must turn to a force that is familiar to all of us, yet in this case plays a decisive role: the gravity of the heated world itself. In our everyday experience, rock is often associated with stillness. A stone by the roadside may remain there through countless seasons of rain and sunshine. A cliff can hold its shape for so long that an entire human lifetime feels like only a brief moment beside it. Even though we know that mountains erode, continents drift, and Earth's crust is always moving slowly beneath our feet, rock still gives us a sense of permanence, something steady and enduring, almost the opposite of things that seem soft and changeable, like water, vapor, clouds, or smoke. For that reason, when we hear that a rocky planet may be evaporating, the idea can feel unfamiliar at first. Yet in nature, no form of matter is truly unchanging. Rock remains quiet only when it exists within an environment gentle enough to keep it in a solid state. Bring it much closer to a star, place it beneath a relentless stream of radiation and extreme heat, and that quiet stability begins to change. At the temperatures we experience on Earth, rock does not easily become vapor. Before reaching that state, many minerals must first melt, break apart, or undergo complex chemical changes. But on a planet orbiting extremely close to its star, the surface exists far beyond the familiar range of Earth's climate and geology. The side facing the star may become so hot that some minerals do more than melt into lava. They can release volatile components into the space above. The atoms and molecules escaping from the surface form a thin layer of mineral vapor, very different from the atmosphere we know on Earth. It is not a pale blue sky rich in nitrogen and oxygen. It is not an atmosphere filled with clouds and weather as we experience them. Instead, it may be a hot, tenuous layer of material carrying traces of heated rock. Sodium, potassium, silicon, oxygen, iron, magnesium, or various mineral compounds depending on the planet's composition. As unusual as this sounds, it is not entirely without familiar parallels. Here on Earth, molten lava reminds us that rock is not always rigid. During volcanic eruptions, material that once lay deep underground can rise to the surface, flow while glowing red-hot, release gases, and eventually cool into new rock. The difference is that on Earth, these processes are usually driven from within the planet itself by internal heat, pressure, magma, and fractures in the crust. On an ultra-close exoplanet, however, the dominant heat source may come from outside. Starlight pours onto the surface continuously. Rather than a single volcano opening in the crust, nearly the entire dayside of the world may become a vast heated landscape where matter constantly shifts between solid, liquid, vapor, and dust. A gentler way to picture this is to imagine a beach after a day of intense sunlight, when the sand holds warmth and the air above it seems to shimmer. The sand is not evaporating, yet you can sense that the material beneath your feet has absorbed and stored energy. Now, extend that image to an extreme beyond anything familiar, where the light does more than warm the ground, it begins to destabilize minerals themselves. The surface may become a sea of magma. Volatile components within the rock may escape as vapor. Then, as that vapor moves away from the hottest regions, it begins to cool. Material that was once part of the surface can condense into tiny particles, much like smoke gradually cooling into fine dust. Within the tail trailing behind the planet, those particles are no longer rock in the form of a solid boulder, yet they still carry the chemical fingerprints of the world that created them. This is one of the reasons disintegrating planets are so fascinating to the study of exoplanets. For most distant rocky worlds, we know only a few basic facts: their size, their orbit, and sometimes their mass and estimated density, if enough data are available. Those numbers can suggest whether a planet is likely rocky, gaseous, or icy, but they rarely reveal exactly which minerals make up its surface. A planet that is shedding dust offers a rarer opportunity. Its material is no longer completely locked beneath the surface. A small fraction is drawn outward, spread into a thin tail, and carried across the face of the star. As starlight is absorbed or scattered in different ways, that tail becomes a faint fingerprint of rock itself. We cannot collect a physical sample by hand, but we can attempt to read its composition through light. Of course, caution is essential here. Saying that a dust tail may reveal a planet's composition does not mean we can always read a clear ingredient list like the label on a laboratory container. Data from distant worlds are often faint, noisy, and dependent on interpretation through models. Under certain conditions, one type of dust grain can produce signals that resemble those of another. Grain size, shape, temperature, distance from the star, and the intensity of radiation all influence how dust interacts with light. For that reason, scientists do not rush to declare that they have identified every mineral with complete certainty. Instead, astronomers build possible explanations, compare models against observations, and gradually narrow the range of compositions that best fit the measured signals. That slow process makes the story more beautiful, not less. Rather than receiving an easy answer, we find ourselves following an extraordinarily delicate trail of clues. A rocky planet so distant that its own light is nearly overwhelmed by its star can, through its gradual disintegration, release dust grains that alter the starlight in measurable ways. Each grain may once have been part of a scorching crust, a piece of a surface, a fragment of a world with its own mass, orbit, and history. Once separated from the planet, it becomes wandering matter. As it passes in front of the star, it becomes a signal. And when that signal reaches a telescope, it becomes a question that human curiosity can pursue. It is also helpful to distinguish between mineral vapor and mineral dust because the two are often blended together in our imagination. Vapor is matter in a gaseous state, made up of atoms or molecules moving more freely. Dust consists of condensed particles large enough to scatter or absorb light in distinctive ways. On an extremely hot planet, material may leave the surface as vapor. Later, as conditions change, some of that vapor can condense into dust. It is usually the dust that creates the elongated and unusual shapes seen in light curves, because it spreads across a much larger region than the planet itself. Vapor can also leave spectral signatures under the right conditions, but the comet-like tails described by many models are typically associated with tiny solid dust particles formed from rocky material that was heated so intensely it could no longer remain on the ground. When viewed this way, an evaporating planet begins to look less like a dramatic catastrophe and more like a very slow transformation of matter. The rock is not vanishing into nothingness. It moves from surface to vapor, from vapor to dust, and from dust into a tail stretching through starlight. Some of it may fall back again, some may be blown away. Some may continue orbiting the star for a time before dispersing. The material still exists, but it no longer belongs to the planet in the same way it once did. In that transformation, we see something deeply fundamental about the universe. Even the things that seem most solid are only temporary states of matter under particular conditions. Returning for a moment to the quiet room where the listener is gradually relaxing, there is a gentle contrast to notice. Beneath our feet, Earth feels stable. The walls around us, the floor below, the roads outside, and the distant mountains all give life a sense of permanence. Yet somewhere out there are rocky worlds placed in conditions so different that this familiar stability can no longer survive. Not because rock is weak, but because the universe contains environments far beyond ordinary human experience. There are places where rock rests quietly in the cold. There are places where it flows as oceans of fire. And there are places where it rises as mineral vapor, becomes dust, and leaves behind a faint tail that resembles the breath of a planet. From this changing state of rock, the story naturally moves toward the next important question. Mineral vapor may rise, and dust may form, but not everything that lifts away is lost forever. On a world with sufficiently strong gravity, material can be pulled back, fall again, condense, and rejoin the surface. The difference between a temporary veil of vapor and a true dust tail lies in whether the material can escape the planet's grasp. So now that we understand how rock can lose its silence beneath the light of a nearby star, we must listen to another quiet force that helps determine the fate of every particle, whether the planet is strong enough to hold on to itself. For a dust grain to leave a planet behind, it must first overcome something remarkably quiet: the planet's own gravity. On large worlds, gravity acts like a broad and steady hand, holding an atmosphere, dust, water vapor, clouds, and many other layers of material close to the surface for immense spans of time. Earth retains its atmosphere not only because it orbits at a suitable distance from the Sun, but also because its mass is large enough to pull most of its air back toward the planet, even though every molecule is constantly in motion. If a gas molecule rises high into the atmosphere, it still remains within Earth's gravitational reach. If a dust particle is lifted by the wind, it can still fall back down. This ability to hold things close gives a planet a sense of wholeness, as though it gently embraces the thin layers surrounding it. A smaller planet does not hold on to material in quite the same way. Its gravity is weaker, the speed required to escape it is lower, and the delicate layers above its surface are more easily disturbed by the environment around them. Within our own solar system, we can see this difference in the contrast between Earth, Mars, and the Moon. Earth maintains a thick and stable atmosphere. Mars, being smaller and less massive, has lost much of its ancient atmosphere over time, partly because its gravity is weaker, and partly because it lacks a global magnetic field to shield it from the solar wind. The Moon is smaller still, possessing almost no true atmosphere at all, only an extremely tenuous collection of particles near its surface. These nearby examples are not perfect analogs for disintegrating exoplanets, but they remind us that a world's ability to retain material always depends on its size, mass, temperature, and the stellar environment surrounding it. On an ultra-hot rocky planet orbiting close to its host star, the weakness of gravity becomes far more important. The surface has already been heated enough to produce mineral vapor and fine dust. The particles above the surface are not influenced only by the planet's downward pull. They are also exposed to forces and disturbances from the outside. Starlight carries radiation pressure, stellar winds stream past as flows of high-energy particles. Tidal forces from the star can distort the region where the planet's gravity dominates. Under such conditions, the gravity of a small planet begins to resemble a thin rope trying to hold onto dust grains in a wind that is simply too strong. The rope does not disappear, but it no longer has enough authority to keep everything in place forever. One concept helps us picture this boundary. Every planet has a region where its gravity outweighs the gravitational influence of its star. For a large planet orbiting far from its star, that region is broader, giving surrounding material more space in which it can still be considered part of the planet. But when a planet lies extremely close to its star, the star's gravity presses in much more strongly, shrinking that safe zone. It is a bit like someone trying to hold onto a cloth in the wind. If the breeze is gentle and the grip is firm, the cloth merely flutters. If the wind strengthens, the edges begin to stretch away. If the grip is not strong enough, part of the fabric slips free. For a planet orbiting close to its star, that cloth is the thin layer of vapor and dust above the surface, while the wind is the combined influence of heat, radiation, stellar winds, and the gravity of the host star. Of course, material does not leave a planet simply because it wants to escape. At the scale of atoms and dust grains, everything depends on energy and motion. When mineral vapor forms above a scorching surface, its atoms and molecules move more rapidly. Some of them may achieve speeds high enough that falling back becomes increasingly difficult. As they rise, they enter regions of lower density, where they can be influenced by starlight, become ionized, be pushed outward, or condense into dust and continue their journey away from the planet. For tiny dust grains, the radiation pressure carried by starlight can become surprisingly important. Light may not feel heavy in everyday life, but it does carry momentum. When it strikes microscopic particles, it can exert a small yet persistent push. Close to a star, that subtle force can gradually alter the paths of dust grains over time. This is why a planet's tail is not simply a stream of material flying straight outward. It is the result of several forces acting simultaneously. A dust grain carries the orbital motion of the planet, feels the pull of the star's gravity, experiences the push of radiation pressure, and may also be affected by stellar winds. The resulting tail can become curved, thin, extended, and constantly changing. Sometimes the dust trails behind the planet as a faint streak. In other cases, material may become distributed unevenly, creating an asymmetric transit signal. Seen from Earth, these details do not appear as a sharp image, but as subtle distortions in a light curve. The starlight may begin fading slightly before or after the planet itself passes across the star, or the dimming may follow a shape that does not resemble the signature of a simple spherical world. This also explains why not every hot planet displays a dramatic dust tail. A larger planet, even if intensely heated, may still retain material more effectively. A planet with a different composition may produce less dust. The activity level of the host star can also strengthen or weaken the process of mass loss. Distance from the star, planetary mass, dust grain size, the rate of material loss, surface temperature, and mineral composition all help determine whether a prominent tail forms or whether only a faint signal remains. The science here is not built on a simple rule that says close to a star means disintegration. The reality is more subtle. A planet must occupy a rather specific set of conditions, where heat is strong enough to create vapor and dust, while gravity is not strong enough to reclaim everything that rises away. Viewed more slowly, each orbit begins to resemble a negotiation between the planet and its environment. The heated surface produces new material in the form of vapor. Gravity pulls that material downward, trying to keep it close. Starlight and stellar winds draw it outward. Some falls back, some continues on. Some becomes dust within the long tail stretching behind the planet. There is no sharp boundary between retention and loss, only a transition zone where each particle follows its own fate. One grain returns to the surface, another enters an orbit around the star. Another happens to pass across the stellar disk while a telescope is watching, leaving behind a tiny change in the light that eventually reaches us. Within that gradual process lies a quiet but profound realization. A planet is not defined solely by the rock that makes up its body, but also by its ability to hold onto what belongs to it. An atmosphere, dust, mineral vapor, and the delicate layers surrounding the surface are all fragile extensions of a world. When gravity is strong enough, they remain in place and help shape geological history, climate, and even the potential for habitability. When gravity becomes too weak in the presence of a nearby star, those layers begin to drift away. The planet itself remains. It still orbits its star. It still possesses a core and a surface, yet its boundaries become less distinct. Part of it no longer lies beneath the imagined feet of an observer standing on the ground, but has become dust moving through space. What makes this image fitting for a slow journey of listening is not destruction, but fragility. Somewhere far away, a small world continues to move along the orbit that gravity has written for it. It has no will with which to resist its star, and no dramatic moment in which it announces its disappearance. It simply exists under conditions that are too extreme, too close to the source of light, too hot for rock to remain entirely at rest, and too light to hold on to every particle that rises from its surface. And with each passage across its star, a tiny piece of that fragility reaches us in the form of missing starlight. Once gravity can no longer keep everything in place, the material leaving the planet begins a life of its own. It does not vanish immediately. It drifts, is pulled, is pushed, cools, condenses into dust, and stretches behind the planet like a faint brushstroke across the bright backdrop of the star. It is here that the most recognizable image of this story finally comes into view. A rocky planet that possesses not only an orbit and a heated surface, but also a tail. That tail makes it resemble a comet, yet its origin is profoundly different. It is not the vapor of ice released from a frozen body approaching the sunday. It may instead be dust made of rock itself, the thin breath of a world that can no longer fully hold on to its own substance. Once material has left the surface and is no longer held tightly by the planet, it does not immediately dissolve into space as an anonymous trace. For a period of time, short or long, depending on the conditions, those tiny dust grains continue traveling along with the world that created them. They are drawn into a faint trail behind the planet, gently curving along its path around the star. From a distance, the image naturally brings to mind a comet, a small object approaching a bright source of light, leaving behind a long, delicate tail that either shines or dims the starlight behind it. But the more closely we look, the more that resemblance reveals an important difference. A familiar comet in our solar system typically carries large amounts of ice and cold dust from distant regions. As it approaches the sun, the ice sublimates into gas and drags dust outward to form a tail. In the case of a disintegrating rocky planet, however, the material does not come from ancient ice. It may come from the rocky surface itself, heated until it begins to vaporize. That distinction makes a planet's dust tail feel both familiar and strange. Familiar, because we have all seen images of comets stretching luminous trails across the sky. Strange, because this tail belongs not to a frozen wanderer arriving from the cold outskirts of a planetary system, but to a rocky world orbiting its star rapidly and at extremely close range. It is not an occasional visitor passing through the inner system. It is a permanent resident of that harsh, brilliant region, circling its star again and again, potentially losing a little more material with every orbit. The tail is therefore more than a decoration trailing behind the planet. It is a sign that the planet's boundary is beginning to open outward, as though the surface no longer ends neatly where rock meets space, but continues into dust, vapor, and a stream of matter guided away by starlight. If we could stand at a safe imaginary distance and observe such a system from the outside, we might picture a dark planet close to its star, one edge glowing intensely under the stellar glare, red-hot fractures visible across a darker rocky landscape. Behind it, space would not be entirely empty. A stream of fine dust would extend outward like an extremely delicate ribbon, not perfectly straight but gently curved along the orbit, gradually fading as it moves farther from its source. Dust close to the planet might be denser and hotter, while dust farther away could cool, disperse, and be pushed into different directions by starlight. In reality, we do not witness this scene directly with our eyes, yet the models and transit observations suggest something very much like it. A small planet that is no longer a solitary point, but a world accompanied by enough material to stretch its shadow across the light of its star. That tail is made of extremely small particles, and their tiny size is precisely what makes them so responsive to outside forces. A large rock that escaped from a planet would follow a relatively straightforward path, shaped mostly by gravity. A microscopic dust grain, however, has a large surface area compared with its mass, making it much more sensitive to the influence of starlight. Radiation pressure pushes it away from the star, while gravity pulls it inward. At the same time, the grain still carries the imprint of the planet's original orbital motion. The result is that the tail does not necessarily remain directly behind the planet in the simple way smoke trails behind a moving vehicle. It can curve, spread outward, shift direction, or change from one transit to the next. This gentle complexity is what gives the light curve its distinctive shape, making it look different from the signature of an ordinary spherical planet. One point is worth explaining carefully to avoid misunderstanding. This tail does not necessarily glow brightly like the illustrations often shown in artwork. In many cases, it is recognized because it blocks light, not because it shines on its own. Dust grains passing in front of the stellar disk can absorb or scatter a fraction of the starlight, creating a dimming signal that extends beyond the physical size of the planet itself. Because the dust is unevenly distributed, the signal is uneven as well. One transit may reveal a thicker tail, another a thinner one. Sometimes the fading extends noticeably behind the planet, while at other times the shape changes because less dust is being produced, or because the dust is being swept away more quickly. From our distant perspective, this activity does not appear as the motion of individual particles, but as subtle variations in the recorded light. For that reason, the word tail is really a tool for the imagination rather than a precise description of a sharply defined structure. In reality, the tail has no clear edge. It has no surface, no distinct boundary, and no abrupt ending. It is a diffuse region of dust whose density gradually decreases with distance. One grain remains closer to the planet, another has drifted much farther away, and another may have fragmented, evaporated, or entered a new orbit around the star. If we could magnify the scene enough to see every individual grain, the tail would no longer appear as a smooth ribbon. Instead, it would become a vast collection of tiny particles following slightly different paths. Yet when viewed together against the light of the star, those countless grains form a soft trace that allows telescopes to recognize that the planet is not traveling alone. Part of what makes this image so compelling is that the tail serves as evidence of a process unfolding in real time, at least on astronomical timescales. When we look at an impact crater on a planet, we are usually seeing the remains of an event that happened long ago. When we examine layers of rock, we are reading history preserved in geological structures. But when we observe a planet with a dust tail, we are witnessing material actively leaving that world. The observations do not simply tell us that the planet changed in the past. They show that it is changing now. Each transit may reveal a slightly different version of the same story. One passage may contain more dust, another less. Sometimes the planet leaves a deeper mark on the starlight. At other times, it becomes almost quiet again. For a journey meant to be listened to before sleep, the image can remain wonderfully gentle. There is no need to turn it into a dramatic spectacle. It can be imagined instead as a faint brushstroke trailing behind a dark point drifting across a field of light. The dark point is the planet. The brushstroke is its own dust. The star behind it is too bright for us to see the small world directly, yet that same light is what allows the tail to reveal itself. Without the star, the dust might remain almost invisible. Without the transit, we might never know it was there. There is a quiet paradox in that relationship. The star is both the reason the planet is losing material and the backlight that allows us to witness that loss. The dust tail also makes the idea of a planet feel less rigid than we often imagine. We tend to think of a planet as a sphere with a clear boundary. The planet inside, space outside. But in extreme environments, that boundary can begin to blur. If an atmosphere expands, if material escapes, if dust stretches millions of kilometers behind the world, then the planet becomes more than the solid rock at its center. It includes, at least for a time, the material that is still carrying the signature of its origin. In that sense, the dust tail resembles the dissolving edge of a world, a place where planet and space are no longer separated by a clean line. From a scientific perspective, that dissolving edge is especially valuable. The surface of a rocky exoplanet is usually hidden from us, too small and too close to its star for direct observation. But when material leaves the surface and spreads into dust, it carries information outward from a place we cannot otherwise reach. The dust tail is like a letter torn into countless tiny pieces and scattered through starlight. We cannot read the entire message from a single fragment. Yet if we gather enough signals, compare observations at different wavelengths, and watch many transits over time, we can begin to reconstruct some of what was written there. The planet's mineral composition, the size of the dust grains, and the strength of the mass loss process can all leave traces in the way the tail interacts with light. And once the dust tail has taken shape in our imagination, another question naturally emerges. The dust has left the planet, but what continues to shape it on its journey? Why does it curve rather than simply spread evenly in all directions? Why does it sometimes appear as a trailing stream, while at other times the observations hint at a more complex cloud of material around the planet? To answer those questions, we must look more closely at the environment near the star itself. Where light does more than illuminate, it pushes. Where stellar winds do more than pass by, they carry charged particles. And where every tiny grain of dust must navigate several forces at once. The tail is not a passive trace. It is a delicate map of the invisible forces surrounding the planet. A dust grain that has just left a planet does not enter a completely quiet emptiness. The space around a star is not a dark room where nothing moves. It is a region filled with light, charged particles, magnetic fields, and gravity. There, even the smallest objects must navigate multiple pulls and pushes at once. For a rocky planet that is evaporating, this is especially important because the tail behind it is not created simply by material escaping the surface. That material must continue to be shaped after it departs. It must be stretched, curved, thinned out, sometimes broken apart, and sometimes guided in directions that are not immediately obvious. It is the environment around the host star that transforms escaping dust into the long trail that telescopes can detect. In everyday life, we tend to think of light as something that allows us to see, while wind is what actually pushes things around. But on the scale of tiny particles, light also exerts a force. Light is made of photons, and each photon carries a small amount of energy and momentum. When light strikes a dust grain, it can transfer some of that momentum like an extraordinarily gentle touch repeated over and over again. For a large rock, the effect is almost negligible. For a microscopic grain of dust, however, with very little mass and a relatively large surface area, radiation pressure can become a genuine influence on its trajectory. The closer the grain is to the star, the more intense the light becomes, and the more significant that quiet push is in shaping its fate. Dust within the tail of a disintegrating planet, therefore, does not simply fall under the influence of gravity. It is simultaneously pulled inward by the star's gravity and pushed outward by the star's light. These influences do not necessarily cancel each other, because their relative strength depends on the size of the grain, its composition, and its location within the orbit. Smaller particles may experience a stronger push from starlight relative to their mass, while larger grains may remain closer to the planet's orbital path for longer periods. If the tail contains a range of particle sizes, it will not behave like a uniform stream of smoke. Instead, it becomes something like a faint symphony of countless trajectories, each grain responding to a different balance between the pull of gravity and the push of light. Alongside starlight, there is also the stellar wind. A star emits more than light and heat. It continuously releases streams of charged particles, protons, electrons, and other components that flow outward into surrounding space. Around our own sun, this flow is known as the solar wind, and it plays a role in creating Earth's auroras when it interacts with the atmosphere and magnetic field. Around other stars, stellar winds can also sweep through the space surrounding nearby planets, particularly those in extremely close orbits. When dust grains or mineral vapor become ionized, meaning they gain or lose electrons and acquire an electric charge, they can be influenced not only by the stellar wind itself, but also by the magnetic fields carried along with it. At that point, the motion of the material is no longer simply a story of gravity and orbital motion. It becomes part of a more complex dance within the plasma environment surrounding the star. This helps explain why a dust tail can change over time. A star is not always perfectly steady. Stellar activity can strengthen or weaken. Active regions on the stellar surface can alter radiation and particle flows, and eruptions of material, if they occur, can significantly disturb the environment around a nearby planet. For worlds orbiting extremely close to their stars, Even modest changes in stellar activity may influence how much dust survives, where the dust is carried, and how long it remains intact before being destroyed or dispersed. As a result, when one transit appears deeper and another shallower, the difference may reflect changes in the amount of material leaving the planet, but it may also reveal changes in how the stellar environment is shaping the dust after it escapes. Tidal forces add another layer of subtlety to the story. When a planet orbits very close to a star, the star's gravity pulls more strongly on the side facing the star than on the side facing away. This difference can stretch the planet slightly, distort the region where its gravity dominates, and make it easier for gas or dust to escape through certain areas. For a small rocky world, the effect does not necessarily tear the planet apart, but it can make the gravitational boundary around it more fragile. Rather than material escaping equally in all directions, some pathways may provide easier routes out of the planet's gravitational grasp. Once the material finds those escape routes, starlight and stellar winds can continue shaping it into a longer and more complex tail. If we picture the situation too simply, we might imagine the tail always extending directly behind the planet, like smoke trailing from a moving object. But an orbit is not a straight road. The planet is constantly falling around its star, while newly created dust begins its journey, carrying the planet's original orbital velocity. At the same time, other forces gradually alter its path. The result is that the tail may curve along the orbit, spread outward farther away from the planet, or create asymmetrical patterns as it passes in front of the star. In some configurations, part of the material may even move ahead of the planet, while another portion trails behind. What we observe during a transit also depends on our viewing angle from Earth. The same physical tail in space can produce very different light curves when seen from different perspectives. Because of all these influences, astronomers do not simply ask whether a planet has a tail. They ask how that tail is shaped. A long, thin trail may suggest that dust grains survive long enough to be carried far from the planet before they disappear. A shorter, denser signal may indicate that the dust is destroyed quickly or remains concentrated near its source. If the dimming is stronger at some wavelengths than at others, that may reveal information about the size and composition of the grains. If the depth of the transit changes over time, the dust production process itself may be unstable. Each detail becomes a clue in a larger puzzle: how hot the planet is, where the dust comes from, how large the grains are, and how the stellar environment is carrying them away. It helps to keep a gentle pace when thinking about these invisible forces, because they can easily become abstract. One way to imagine them is to think of fine dust floating in a room where sunlight enters through a window. When the air is still, the particles drift slowly. When a faint current of air passes through, they change direction, swirl, spread apart, and gather into patterns with no clear edges. We do not see the air itself, but by watching the dust, we know that something invisible is moving through the room. Around a star, astronomers do something very similar. They do not directly observe every force acting on the tail. Instead, they study how the dust alters the starlight and how those changes evolve from one transit to the next, allowing them to infer the invisible flows shaping the material. What makes the dust tail so beautiful is that it serves both as a trace of the planet and as a record of the environment surrounding the star. If the planet were merely hot, material might rise from the surface without forming a long tail. If the star's light were powerful but no material escaped, there would be no tail to observe. The tail appears where these two conditions meet: a world that can no longer hold onto all of its material, and a star strong enough to sculpt that escaping material into a visible structure. It belongs entirely to neither one. It is the product of their interaction. For hours, days, or perhaps longer, that material exists in a region between two worlds, no longer part of the planet, yet still recognizable as an extension of it. The fragility of dust also reminds us that the observations capture only a moment in time. A dust grain may be heated further and evaporate. It may collide with another grain. It may disperse until it no longer has any significant effect on the starlight. It may be drawn into new paths around the host star and gradually blend into the surrounding environment. The tail is therefore not a permanent structure like a large planetary ring or the stable orbit of a moon. It is a stream of material that is being created and lost at the same time. If the planet stops producing dust, the tail may fade. If evaporation intensifies, the tail may grow thicker. This temporary nature is one reason the signals from disintegrating planets often vary, and one reason they are so valuable. We are witnessing a process in motion, not merely a structure frozen in place. From the listener's perspective, it may be worth letting this image settle for a moment. A small planet circles its star, unable to hold onto every grain of hot dust rising from its surface. Starlight gently pushes each particle. Stellar winds sweep past. Gravity guides them into broad, curving paths. All of it unfolds in silence. There is no sound, no storm in the way we experience storms on Earth. Only the motion of tiny particles within a region flooded with intense light. Then, at a point unimaginably far away, a telescope notices a subtle change in starlight and begins reconstructing the scene. In that sense, the tail is not merely something the planet leaves behind. It is the way the universe turns invisible forces into a trace that can be read. And once we understand that starlight and stellar winds are shaping the dust, the story moves to a deeper level of observation. If the tail interacts with light, it does more than simply dim the star. It can alter the light differently at different colors and wavelengths. Within those tiny differences, the dust begins to reveal clues about its size, composition, and origin. A dust tail, therefore, is more than the fading shadow of a planet losing material. It can become a remarkably delicate text written in light, waiting for telescopes to read it line by line. There is a quiet beauty in the way humanity observes distant planets. Most of the time, we do not see them directly. We do not see their true surfaces, the color of their rocks, or the dust escaping from the heated edge of a small world. What reaches us is usually only the light of the host star after it has traveled across an immense stretch of space. Within that stream of light, a planet's dust tail leaves behind only the faintest alteration, like a thin veil of smoke drifting across a distant lamp. If the smoke is dense, the lamp appears dimmer. If it is thin, the change in brightness is barely noticeable. If the particles vary in size, the colors of the light passing through can change in subtle ways as well. A telescope does not need to touch the dust, nor does it need to travel close to the planet. It simply measures, with great patience, how the tail changes the light that passes through it. The starting point remains the light curve. When the planet and its dust tail cross in front of the host star, the amount of light reaching the telescope decreases. But instead of producing the neat dip expected from a round planet, the tail creates a softer, more asymmetric pattern that may continue even after the planet's main body has already passed. If most of the dust trails behind the planet, the starlight does not immediately return to normal. Instead, it recovers more gradually, as though a thin mist were still drifting across a distant lamp. If the material is distributed in a more complex way, the signal itself may become asymmetric, giving the light curve a unique shape that no longer resembles the familiar signature of a stable world. Light is more than brightness alone. It also carries color, or more precisely, many different wavelengths. A star emits radiation across a broad range, extending from the visible light our eyes can see into the infrared and beyond. When that light encounters dust, the particles do not block every wavelength equally. The size, composition, and structure of the grains all influence whether light is absorbed, scattered, or allowed to pass through. Very small particles may affect shorter wavelengths more strongly, while larger particles can dim light in a more uniform way. As a result, observing a transit at multiple wavelengths allows astronomers to see the tail not merely as a dark streak, but as a layer of material with its own physical properties. Spectroscopy is the tool that turns light into information. In simple terms, it involves separating light into its different components, much like white light passing through a prism and spreading into a spectrum of colors. In astronomy, a spectrum is more than something beautiful, it is a fingerprint of matter. Atoms, molecules, and dust grains interact with light in different ways. Some materials absorb strongly in one region of the spectrum and weakly in another. Certain minerals leave particularly useful signatures in the infrared, where warm material can imprint faint but measurable features onto the light. If the dust tail is thick enough, if the star is bright enough, and if the telescope is sensitive enough, the light passing through that cloud of dust can begin to reveal clues about what the dust is made of. Yet reading a dust tail is not like reading words clearly printed on a page. It is more like studying a thin layer of smoke through several panes of glass and trying to determine what the smoke contains. Data from distant planetary systems always come with limitations. The star itself may vary slightly. Instruments introduce noise. The amount of dust surrounding the planet may change from one orbit to the next. The dust may consist of multiple particle types mixed together, each with different sizes, temperatures, and compositions. For that reason, scientists do not rush to turn a small signal into a sweeping conclusion. Instead, they build models, test multiple possibilities, compare simulated light curves with real observations, and gradually narrow the range of explanations that best fit the data. That caution does not make the story less fascinating. If anything, it makes the dust tail more elegant. A disintegrating planet does not send us a complete message. It offers only tiny fragments of an ongoing process, a small amount of missing light, a subtle difference between one wavelength and another, one transit that is slightly deeper than the last, a fading signature that extends beyond the planet's physical shape. Each clue is like a fine pencil mark on an almost blank page, and science must learn to read those marks through patience rather than certainty. The infrared region of the spectrum is particularly valuable in this story because warm dust and certain mineral materials often leave clearer signatures there. Human eyes cannot see infrared light, but telescopes can measure it. For disintegrating planets, observations in this part of the spectrum help scientists search for evidence of hot dust, especially dust that originates from rocky material. Modern observatories such as the Content Reference Onasite 0 Index equals 0 provide a far more sensitive view into this realm of light, where a dust tail may appear not merely as a shadow, but as a source of clues about its composition. Even so, the signal remains extremely faint compared with the overwhelming brightness of the host star, which means every conclusion must remain grounded in the limits of the data. One way to imagine the process is to think of listening for a very quiet sound in a room filled with loud music. The star is the music, bright, powerful, and dominating almost all of the available information. The planet and its dust tail contribute only a tiny change, like a faint tap somewhere in the background. The telescope records the entire performance, while astronomers search for the repeating disturbance that appears at the same point in the orbit. If that faint signal arrives precisely when the planet crosses the star, if its shape is stable enough to distinguish from noise, and if it changes with wavelength in a meaningful way, then the dust tail begins to develop a voice of its own. Not a voice made of sound, but one written in the delicate dimming of light. The dust tail serves two roles at once. It blocks a portion of the starlight, revealing that material extends far beyond the planet itself. At the same time, it filters that light in distinctive ways, helping us learn what that material might be. If the dust consists of extremely small grains, the color-dependent signal may follow one pattern. If it is made of heat-resistant minerals, it may survive longer near the star. If the material is more volatile, the tail may be shorter and change more rapidly. If evaporation becomes more intense, larger amounts of dust may be produced, creating deeper dimming events. No single clue stands alone. They overlap, blend with noise, and gradually emerge only through repeated observations. This is what makes a disintegrating planet valuable in such a unique way. Many other rocky exoplanets may be larger, more stable, or located in less extreme orbits, yet their surfaces remain hidden from view. They do not easily reveal what they are truly made of. An evaporating planet is different. As it loses part of its outer layers, it unintentionally carries material outward from a place that would otherwise be almost impossible to study directly. The dust tail becomes a sample that requires no spacecraft landing, no drill reaching the surface, and no return mission carrying rock back to a laboratory. It simply passes through the light of its own star and leaves behind a faint imprint in the data. There is a gentle paradox hidden within that light. The less capable a world is of holding on to itself, the more opportunity we have to understand it. If the planet were completely stable, its surface might remain silent to our telescopes. But when it begins to lose material, dust and mineral vapor become a language. The star is so bright that the planet nearly disappears from direct view, yet that same light shines through the tail and turns dimming into information. The distance is so vast that we can never reach out and touch the world itself, yet the photons that pass through its dust continue their journey, carrying a trace of the place where they encountered matter. In that sense, the dust tail is more than the extension of a planet that is slowly losing material. It is a place where rock, light, and data meet. Within it may be grains that once belonged to a scorching surface, tiny fragments of minerals that once rested quietly on a distant world. They do not tell their story through words, nor do they appear as a clear image. They alter the light by only the smallest amount, subtle enough to overlook, yet real enough for us to recognize that within that faint trace may lie the chemical memory of a rocky planet. Within the faint tail trailing behind a disintegrating planet, dust is more than dust in the ordinary sense. It is not like the thin layer that settles on a tabletop, nor like the fine ash left behind after a fire on Earth. These tiny particles may once have been part of the planet's surface. They may have spent countless orbits exposed to the glare of their star, carrying within them the mineral composition of a world that humans can never observe directly. Once they leave the surface, they are no longer mountains, bedrock, or an intact crust, yet they still preserve the chemical traces of the place that created them. That is why a dust tail does more than reveal that a planet is losing material. It may also reveal what that planet is made of. For the rocky worlds of our own solar system, humanity has many ways to study composition directly. We have rocks on Earth to examine in laboratories. We have samples returned from the Moon. We have spacecraft orbiting Mars, landing on its surface, analyzing soil, measuring the atmosphere, photographing rock layers, and monitoring dust and ice. Even for Mercury and Venus, where exploration is more difficult, we still have data from flybys, radar observations, spectroscopy, and other measurements. But for a rocky exoplanet, tens or hundreds of light years away, everything becomes far more uncertain. Most of the time, we know only its size, the length of its orbit, and sometimes an estimate of its mass and density. Those numbers can suggest whether a world is rocky or gaseous, but they rarely open a detailed window into the minerals that make up its surface. A disintegrating planet offers a rare exception. As dust escapes and passes through the light of its star, material that was once hidden on a distant world suddenly becomes capable of leaving a measurable signal. If that dust absorbs or scatters light in ways consistent with certain groups of minerals, scientists can begin constructing a picture of what it contains. The dust may be rich in silicates, the family of materials that make up much of the rocky matter found on planets. It may carry traces of magnesium, iron, oxygen, silicon, or other heat-resistant compounds. These names do not need to become a lesson in chemistry. What matters more is the feeling behind them. Within that thin trail of dust may be tiny fragments of a real rocky world, drifting across starlight and quietly revealing something about its nature. The word silicate deserves a gentle introduction here because it appears so often in discussions of rock. On Earth, Many minerals within the crust and mantle are built around combinations of silicon and oxygen, joined with elements such as magnesium, iron, calcium, or aluminum. Similar materials are thought to exist on many other rocky bodies throughout the universe. When scientists consider dust originating from a heated rocky planet, they often focus on minerals capable of surviving extreme temperatures, condensing into grains, and producing detectable signatures in starlight. If a particular material vaporizes too easily, it may not survive long enough near the star to contribute significantly to a long dust tail. If a mineral is more resistant to heat, it may persist longer in that harsh environment and leave a stronger imprint on the signals observed by telescopes. In that sense, the dust tail becomes a natural laboratory. No scientist places samples into a furnace there. No hand crushes minerals into powder and releases them into starlight. The planet and the star perform the experiment themselves. The star provides the heat. The planet provides the material. Gravity, stellar winds, and radiation pressure pull matter away from the surface. Then light passes through the resulting cloud of dust and carries information back to our telescopes. From our perspective, it is an experiment that cannot be controlled, only observed. Every transit becomes another repetition of the process, not identical to the last, but similar enough to leave behind a chain of clues. There is also something beautiful in the way dust preserves memory. A grain of dust does not tell its history through words. It cannot explain how deep it once lay, whether it came from the crust or from material closer to the surface, how long it endured intense heating, or whether it escaped during a period of strong or weak mass loss. Yet its composition is a kind of memory all the same. If it is rich in a particular mineral, that tells us something about the material from which it originated. If it has a certain size, that relates to the processes of condensation and fragmentation within the stellar environment. If it survives long enough to become part of a visible tail, that suggests it can withstand heat and radiation for a meaningful period of time. The memory carried by dust is not conscious memory. It is physical memory, matter retaining traces of the conditions that formed it. At the same time, it is important not to let curiosity outrun certainty. A dust tail does not provide a complete cross-section of a planet. It may be biased toward materials that escape more easily, condense into dust more readily, or survive longer near the star. If deeper layers of the planet never reach space, we cannot read them through the tail. If a particular mineral is destroyed too quickly, it may leave little or no trace in the observations, even if it once existed on the surface. And if the dust changes after leaving the planet, its measured composition may no longer perfectly reflect the original material. The tail is therefore a valuable window, but not a fully open door. It reveals part of a world, not the whole of it. That limitation makes the story feel closer to real science. Science does not require immediate and perfect answers in order to be meaningful. Sometimes progress comes from adding a small patch of light to a region that was once entirely dark. Before astronomers began observing disintegrating planets, studying the surface composition of rocky exoplanets was extraordinarily difficult. Dust tails provide an additional perspective, even if the observations remain challenging, noisy, and dependent on repeated measurements and careful modeling. A small amount of escaping dust can help distinguish between competing ideas about composition. A feature in the infrared may make one explanation more plausible than another. A change in transit depth may hint that mass loss is not occurring at a constant rate. Piece by piece, the picture becomes less empty. You might imagine the tail as an extremely thin river of dust flowing away from the planet's heated edge and gradually dissolving into starlight. This river carries no water, it carries mineral grains. It does not flow through valleys or across landscapes. It moves through space itself. It makes no sound, reflects no moonlight, and has no clearly defined banks. Yet with the star's light behind it, the river casts a faint enough shadow to be measured. Within that shadow, astronomers search for clues, large grains or small grains, darker dust or brighter dust, heat-resistant materials or more volatile ones, compositions that resemble known minerals within their models. Every answer comes with uncertainty, but every answer also reveals another small part of the planet. This perspective also changes the way we feel about a world that is slowly disappearing. If we focus only on loss, the tale becomes a sad reminder of a planet that can no longer hold itself together. But through the lens of science, the tale is also a revelation. The material leaving the planet is no longer hidden in the darkness of distance. It enters the light quite literally and becomes something that can be studied. A stable planet may keep its composition concealed behind the overwhelming brightness of its star. A disintegrating planet, though more fragile, exposes tiny pieces of itself. In that loss exists a kind of information that we rarely receive from distant rocky worlds. The more we think about it, the more the dust tale seems to sit at the boundary between geology and astronomy. Geology speaks of rock, minerals, crusts, heat, pressure, and the formation of planets. Astronomy speaks of light, orbits, stars, distance, and remote observations. Here, those two disciplines meet within a remarkably thin stream of dust. The material belongs to the geology of a distant world, yet our knowledge of it comes through astronomy. Rock becomes absorbed light. Minerals become patterns in a data curve. The surface of a planet becomes a signal recorded by a telescope. That intersection gives the subject a special depth. To understand a single dust grain, we must consider both the planet that produced it and the star illuminating it. In the quiet rhythm of this story, the image that remains is a trail of dust carrying the memory of rock. Those tiny grains may not survive for long. They may be heated further, pushed away, broken apart, or absorbed into the environment surrounding the star. Yet during the brief time they pass through the starlight, they accomplish something that the intact planet itself may never be able to do. They reveal a portion of the world's actual material. Because of them, a distant rocky planet becomes more than a radius, an orbital period, and a catalog entry. It begins to acquire texture. It begins to have dust, minerals, and faint traces of a real surface. And within those subtle traces, humanity can listen to a very small fragment of the story of rock dissolving into starlight. During the years that the Kepler Space Telescope quietly watched a fixed patch of sky, it did not search for planets through the kind of close-up images we often imagine. It could not photograph tiny worlds drifting around distant stars, nor could it see their rocky surfaces or atmospheres in any way recognizable to the human eye. Instead, it measured light. Day after day, it monitored the brightness of thousands of stars, waiting for those subtle moments when the light dimmed slightly as a planet passed in front of its host star. In most cases, if the signal was clear enough, it followed a predictable rhythm. The light faded a little, remained lower for a short time, and then returned to normal. A stable world usually leaves behind a stable shadow. But every so often, hidden within that orderly stream of data, there appeared shadows that refused to behave that way. One of the most famous examples of such an unusual signal is Kepler 1520b, once known by its observational designation, KIC 12557548b. Its name may sound dry and difficult to remember, as many names in modern astronomy do. But what made this small world remarkable was never its name. It was the way the light of its host star changed. The transits were not identical. Sometimes the dimming was deeper, sometimes shallower, and at times the signal nearly faded to the point of becoming difficult to detect at all. If a solid, spherical, and stable planet were crossing the star along the same orbit each time, we would expect its shadow to repeat in a much more consistent pattern. This irregularity encouraged astronomers to look more carefully, more patiently, and to ask whether something beyond the planet itself might be blocking the light. The idea emerged not from a spectacular image, but from a subtle inconsistency in the light curve. If a small object is surrounded by dust, its shadow is no longer as clean as the shadow of a simple sphere. Dust can spread behind the object, change in density, dissipate, and be replenished from one orbit to the next. When more dust is present, the starlight is blocked more deeply. When less dust exists, the dimming becomes shallower. If the tail stretches farther behind the planet, the star's brightness may recover more slowly after the planet's main body has already left the stellar disk. From a great distance, none of this appears as a beautiful dust trail against the sky. It appears only as an uneven signal, a shadow that seems too soft and too variable to belong to an ordinary planet. It is here that the picture of a disintegrating world begins to gain its power. This small planet orbits extremely close to its star, completing a full revolution in less than a single Earth day. At such a short distance, the surface is exposed to intense radiation. If the object is a small rocky world, the heat may cause surface material to vaporize into mineral gas, which later condenses into dust as it moves away from the hottest regions. The planet's weak gravity cannot hold onto everything. Starlight and the surrounding stellar environment draw the dust behind it, creating a thin trailing tail. No explosion is required. No catastrophic collision is needed. Through nothing more than the repeated effects of heat, orbital motion, and gradual mass loss, a planet can begin leaving behind grains of its own substance. What makes this discovery so valuable is that it demonstrates how science often begins with a feeling that something does not quite fit. The data did not immediately announce that a planet was evaporating. They merely showed a pattern of dimming that was difficult to explain with a simple model. Astronomers had to consider many other possibilities. Could the star itself be varying in brightness? Could the signal be instrumental noise? Could another object in the system be responsible? Or was a cloud of dust distorting the light curve? Only when the idea of a small object trailing a dusty tail successfully explained multiple features of the observations did the picture of a planet losing material become the most convincing interpretation. That caution makes the story quieter, but also deeper, because it shows how an extraordinary conclusion can emerge from very calm measurements. From this case, astronomers realize that planetary disintegration does not necessarily proceed at a steady pace. If the dust originates from a heated surface, the amount of dust produced may vary according to geological conditions and the stellar environment. A region rich in more volatile material might generate dust more efficiently. A period of increased stellar activity could sweep dust away more quickly. Grains of different sizes may survive for different lengths of time before they are heated further, dispersed, or carried out of view. In that sense, the changing shadow is not a weakness of the explanation. It is exactly what we would expect from a dust tail that is constantly being created and constantly being lost. You might imagine this world as a small stone placed too close to a giant lamp, but even that image does not fully capture its reality. It does not sit still while slowly wearing away. It continuously falls around its star in a rapid orbit, held by gravity, heated by starlight, and followed by a veil of dust that grows thicker or thinner over time. Close to the star, newly formed dust may still be hot and relatively dense. Farther away, it becomes more diffuse, stretched by radiation pressure and stellar winds. To the naked eye, everything would likely be overwhelmed by the brilliance of the star itself. Yet within the data, the dust leaves behind its own distinct rhythm, like an unsteady brushstroke moving across the face of the star. The fascination of this story does not come from the idea that the world will disappear tomorrow. On human timescales, the process may continue for a very long time, but on astronomical timescales, catching a planet during a phase of significant mass loss is uncommon. Most planets we know either remain stable in their orbits or conceal their internal processes in ways that are difficult to observe. A disintegrating planet occupies a rare middle ground. It still contains enough material to be recognized as a planet, yet it is lost enough that its dust tail becomes visible. It is like a transitional moment stretched out across the universe, one that a telescope happened to witness through starlight. In the history of exoplanet discovery, Kepler opened an immense map of worlds orbiting other stars. Some are larger than Jupiter. Some are super-Earths. Some belong to multi-planet systems whose transits repeat with almost clock-like precision. Among all those signals, this disintegrating world occupies a quieter but uniquely intriguing corner. It does not immediately evoke thoughts of habitability or distant oceans. Instead, it suggests something different. Planets are not always stable spheres that remain unchanged for immense periods of time. Some worlds are recognized most clearly not when they exist in a complete and steady form, but when they are changing, losing material, and allowing starlight to redraw their boundaries. That unusual shadow, therefore, became a small turning point in how we imagine rocky exoplanets. Before discoveries like this, a distant planet was often represented by a handful of numbers: radius, orbital period, estimated mass, and distance from its host star. After signals like these, planets began to acquire a more physical presence. They might possess surfaces heated to extremes. They might contain rock turning into vapor. They might trail streams of dust behind them. Their transits might vary because their own material is helping to block the starlight. These details transform a simple data point into a world with processes, an environment, and ongoing change. When the image finally settles in the mind, what remains is not the long catalog designation of a distant planet, but an uneasy shadow crossing a star. A small world moves through a field of light. A dust tail follows behind it, sometimes more visible, sometimes less. A light curve refuses to repeat itself in exactly the same way each time. From those delicate clues, humanity began to recognize that some rocky worlds are not merely existing out there in the darkness. They are slowly dissolving into starlight, gradually enough for the universe to preserve the process, and clearly enough for telescopes to listen to it through light. Not every dust tail, trailing a disintegrating planet, has a shape that is easy to picture as a neat stream stretching behind it. In simple illustrations, we often see the planet leading the way while dust extends behind it like the tail of a comet. That image offers a useful introduction, but nature is usually more complex and more subtle than a graceful curve painted across a dark background. When dust escapes from an intensely heated planet, it does not merely inherit the planet's motion. It is pushed by starlight, pulled by the star's gravity, disturbed by stellar winds, and may even be produced unevenly from different regions of the surface. As a result, the tail is not always a simple trail behind the planet. It can shift to one side, spread outward, curve along the orbit, or even leave hints that material exists both ahead of and behind the world itself. One example that helps bring this picture into focus is K2, 22b, an exoplanet orbiting extremely close to its host star. With its short orbit and unusually variable transit signals, it has drawn attention as another candidate world losing material. Like other disintegrating planets, it does not appear as a crisp sphere in a telescope image. What astronomers see is starlight changing in ways that are not entirely regular. Certain features of the signal suggest that the dust surrounding the planet may not simply trail behind it in a straightforward manner, but could be distributed more intricately around its orbit. The light may begin to fade a little differently than expected, or recover in a pattern that lacks symmetry. It can be imagined as a thin veil of smoke near a flame, not drifting in a single stream, but being pulled into delicate, shifting patterns by several gentle currents at once. Far from diminishing the beauty of the dust tail, this complexity brings the image closer to real physics. A dust grain that has just escaped the planet still carries the planet's rapid orbital velocity. It does not sit motionless in space waiting for starlight to push it away. It is already racing around the star, along with the world that produced it. Once it escapes the planet's gravitational hold, the grain enters a dance governed by multiple forces. The star's gravity pulls it toward a new trajectory. Radiation pressure nudges it outward. Stellar winds and magnetic fields can make the motion of charged particles even more complicated. Larger grains may remain close to the original orbit for longer periods, while smaller grains respond more strongly to starlight. Tiny differences like these accumulate over time, causing the cloud of dust to behave less like a uniform stream and more like a collection of individual paths woven together. For that reason, the tail should not be imagined as a solid structure with a fixed shape. It is not a rope tied to the planet, nor a streak of paint neatly dragged behind it. It is a diffuse region of material that is constantly being replenished and constantly being dispersed. Newly formed grains near the scorching surface may be relatively dense. Older grains that have drifted farther away may become more sparse, heated further, scattered apart, or diluted until they can no longer block light in a measurable way. Some dust may occupy positions that place it slightly ahead of the planet from Earth's perspective, while other material stretches behind it. When this entire structure passes in front of the host star, the resulting dimming depends not only on the planet itself, but also on the blurred and changing shape of the surrounding dust. If a perfectly round planet crosses its star, the light curve tends to resemble a fairly symmetrical dip. But if material exists both ahead of and behind the planet, that shape changes. The starlight may begin to fade before the planet itself reaches the point of greatest obscuration because dust in front has already crossed the stellar disk. Or the light may return to normal more slowly because dust behind the planet continues to dim the star after the planet has passed. The depth of the transit may also vary from one observation to the next if the amount of dust being produced changes over time. In the data, these effects resemble a rhythm of light that is not quite steady, and it is precisely that irregularity that becomes a clue to the motion of matter around the planet. This small world reminds us that disintegrating planets are not identical copies of the same phenomenon. Every planetary system has its own conditions. Each host star has its own temperature, brightness, and level of activity. Each planet has its own mass, size, composition, and orbit. The dust itself may consist of different kinds of grains, produced at different rates and surviving for different lengths of time. As a result, even though these worlds all show signs of losing material, each may draw a different kind of tail in the light of its star. Some leave behind a long, obvious trail. Others produce only a faint haze. Some create signals that vary dramatically from one orbit to the next. Others require astronomers to test many different models before understanding where the dust might actually be located. The universe rarely repeats a beautiful image in exactly the same way everywhere. Instead, it offers variations. One planet may shed dust like smoke drifting behind it. Another may spread material throughout part of its orbit. In one system, dust survives long enough to form an extended tail. In another, it is destroyed so quickly that the signal becomes brief and highly variable. One host star may be relatively calm, allowing the tail to remain more stable. Another may be more active, causing the structure to change continually. The underlying process remains the same: rock heats up, material escapes, and dust interacts with light. But each planetary system gives that process its own appearance. In cases like these, a telescope performs something like the art of listening through light. Astronomers do not simply ask whether a planet exists. They observe many transits, comparing one passage with the next. They examine whether the dimming begins earlier or later, whether it is deeper or shallower, whether it appears symmetrical or skewed. They observe at different wavelengths to understand how the dust affects the light. They test models with trailing tails, leading clouds, large grains, small grains, heat-resistant materials, and more volatile substances. Each model is a different way of arranging an invisible cloud in the imagination and then asking which arrangement produces a shadow that most closely matches reality. Even so, caution remains essential. When scientists suggest that dust may exist ahead of or behind a planet, they are not looking at direct photographs of individual grains. These interpretations emerge from the shape of the light and from different dust structures can sometimes produce similar signals, especially when the data contain noise or when the star itself undergoes slight variations. Scientific confidence usually grows slowly, through repeated observations and multiple independent tests. Rather than forcing the universe to resemble an illustration, astronomers allow the light itself to reveal how complex the true dust tail may be. You might imagine this planet as a small ember racing around a giant flame. Fine dust is continually blown from its surface, yet no single current determines its fate. Some grains remain close to the orbital path, others are pushed farther away. Some are heated until they cease to exist as solid particles. Others drift into positions where they can block starlight even before the planet itself arrives. From Earth, we see neither the ember nor the individual grains of ash. We see only the flame behind them dimming in an unusual way. That subtle oddness is enough to tell us that something broader than the planet itself surrounds it, something softer than a solid surface and more dynamic than a stable orbit. Once we become familiar with the image of a rocky planet trailing a comet-like stream of dust, cases like this broaden the picture. Dust does not always remain behind. It can surround the planet, drift to one side, be pulled in multiple directions, and create a wide variety of signatures in starlight. The tail ceases to be a static brushstroke across the darkness of space. Instead, it becomes a cloud of matter that is constantly being rewritten, born from heated rock, released into the star's gravitational influence, gently pushed by light, disturbed by stellar winds, and finally revealed to telescopes as an asymmetric shadow. Within that asymmetry, we glimpse something fundamental about nature itself. It never creates only one version of a phenomenon. Every disintegrating planet offers its own way for matter to leave a world. Every dust tail becomes a unique drawing made by light, gravity, and drifting grains. Some stretch behind the planet like an almost invisible stream of smoke. Others spread around the orbit in shapes that resist simple description. Yet in every variation, the planet continues its journey around the star, holding onto what remains of its core while allowing a small part of itself to drift into the light. When looking at a dust tail stretching behind a disintegrating planet, it is easy to feel as though the world is living through the final moments of its existence. The image of rock turning to vapor, material escaping into space, and starlight steadily eroding the surface suggests a process of irreversible destruction. Yet the universe often operates on timescales far removed from human intuition. A process powerful enough to reshape a planet can still unfold over immense spans of time when viewed against the backdrop of millions or billions of years. So when astronomers observe a world losing material, one of the most natural questions arises: just how fast is it happening? At first glance, the dust tail can create the impression that the planet is pouring enormous amounts of material into space. In reality, the mass being lost, while significant in astronomical terms, is often very small compared to the total mass of the planet itself. Imagine a vast mountain slowly shedding grains of sand to the wind. If you focus only on the grains in motion, the loss seems obvious and continuous. But if you look at the mountain as a whole, the change over a single day is almost impossible to notice. Disintegrating planets are much the same. They may lose material during every orbit, yet enough of the world remains for it to survive across extraordinarily long periods of time. Of course, not all planets are alike. A small world containing only a tiny fraction of Earth's mass will respond differently than a larger one. If the amount of escaping material represents a substantial fraction of the planet's total mass, its evolution may proceed more rapidly. In extreme cases, a planet could gradually lose much of its outer layers, leaving behind a remnant far smaller than it once was. Even then, however, rapid in astronomy often means something very different from what it means in everyday life. A process lasting millions of years may be considered brief on the timescale of planetary systems. What makes these worlds especially intriguing is that astronomers are interested not only in how much material they are losing today, but also in their history. Has the planet always been as small as it appears now, or was it once much larger? Is the dust tail we observe today the signature of a long, drawn-out final stage, or merely a short chapter within a much longer story? These questions are extraordinarily difficult to answer directly because they involve timescales far beyond the lifespan of any observing program. No one can wait millions of years to watch the entire process unfold. Instead, scientists combine present-day observations with physical models to imagine the evolutionary paths that may have led to the world we see today. One possibility is that some of the disintegrating planets we observe now are the remnants of worlds that were once substantially larger. Long ago, they may have contained much more material. They may have possessed thicker outer layers or experienced conditions very different from those we observe today. After enduring intense radiation from their host stars over countless short orbits, they gradually lost part of themselves and evolved into the state that modern telescopes now detect. If that picture is correct, then the dust tail is not merely a story about the present. It is also the surviving trace of a history that began long before humanity ever knew the star system existed. In some ways, these planets resemble sea cliffs on Earth. Standing before a cliff worn away by waves, you may see small fragments of rock falling and recognize that the coastline is changing. Yet the cliff's present shape is the result of countless waves that arrived long before that moment. What you witness today is only a tiny part of a much larger story. For a disintegrating planet, the dust tail serves a similar role. It is the visible portion of a process that began long before any telescope was pointed toward its star. Models suggest that the rate of mass loss can vary dramatically, depending on temperature, planetary mass, composition, and the activity of the host star. A smaller planet may lose material more readily. A world rich in minerals that vaporize more easily may generate dust more efficiently. A highly active star may create a harsher environment around the planet. There is no single number that applies to every case. Each planetary system is like its own natural experiment, beginning with different conditions and following its own evolutionary path. This is one reason why disintegrating planets occupy such a special place in exoplanet research. They do more than reveal the current state of a world. They hint that planets may change far more dramatically than we once imagined. For many years, planets were often pictured as relatively stable structures after their formation. They orbited their stars, cooled or retained heat, occasionally experienced collisions, but generally persisted in roughly the same form for immense spans of time. Worlds that are actively losing material remind us that there are environments where planets do not merely exist, they are continually being reshaped by the influence of their own stars. Viewed more broadly, this idea echoes something familiar throughout the universe. Very little remains truly unchanged. Stars evolve as they age. Galaxies transform through collisions and mergers. Gas flows through molecular clouds, young stars, and the remnants of stellar deaths. Even planets, which often feel permanent and enduring, can pass through periods of loss and transformation. In that sense, a dust tail is more than an unusual phenomenon. It is a reminder that matter throughout the cosmos is always in motion, differing only in the pace of its change. In the quietness of space, a small world continues its journey around its star. With each orbit, a tiny amount of material may leave its surface. Newly formed dust joins the tail already trailing behind it. Older grains gradually disperse and disappear from view. The process has no beginning that we personally witnessed, and no ending that has yet been observed. It is simply happening, much as waves continue to shape a coastline whether anyone is there to watch or not. Perhaps that is what makes disintegrating planets so captivating. They are not worlds being destroyed in a single dramatic instant. They are more like very long stories written in dust, light, and time. Each transit is only a single line within that story. Each dust tail is merely a brief glimpse of a process unfolding across countless orbits. And when we look at the material leaving the planet, we are not only witnessing loss, we are witnessing astronomical time itself, taking on a form that can be measured through light. A disintegrating planet may sound like an exception so strange that it sits at the far edge of astronomy. a place where every condition is more extreme than anything humans have ever experienced. It orbits too close to its star, too hot for its surface to remain at rest, too small to hold onto every particle rising from it. Yet exceptions like these often deepen our understanding of things that seem familiar. To understand what a rocky planet truly is, it is not enough to look only at worlds that are stable and relatively cool. We must also examine places where rock is pushed to its limits, where atmospheres cannot endure, and where surfaces become so intensely heated that material begins to escape. Under such extreme conditions, the physical rules that are often hidden within ordinary circumstances become easier to see. Earth, Venus, Mars, and Mercury are all rocky planets, yet each has followed a very different history. Earth retained its oceans, atmosphere, and a surface that has remained active for immense spans of time. Venus developed a dense, scorching atmosphere, becoming a powerful example of an extreme greenhouse effect. Mars, smaller and colder, once hosted liquid water on its surface but gradually lost much of its atmosphere over time. Mercury orbits closest to the Sun, experiencing dramatic temperature swings while possessing almost no substantial atmosphere at all. When we place these worlds alongside disintegrating exoplanets, we begin to see a broader spectrum of possible destinies for rocky planets. Some retain their outer layers, some gradually lose their atmospheres, some become so intensely heated that even rock can no longer remain quietly in place. This comparison is not meant to suggest that Earth is following the path of an evaporating planet. Earth exists in a completely different environment, at a different distance from its star, with a different mass, a different history, and a unique combination of protective conditions. The value of these ultra-hot worlds is not that they serve as direct warnings. Rather, they expand our frame of reference. They show us what can happen when a rocky planet is placed too close to its star. They clarify the roles of orbital distance, gravity, surface composition, stellar activity, and atmospheric retention. By studying extremes, we gain a deeper appreciation for balance. A rocky planet is not merely a solid sphere. It is the result of an intricate combination of interior material, crust, surface conditions, atmosphere, orbit, and host star. Change only a few of those factors, and its fate can be dramatically different. A planet slightly closer to its star may become significantly hotter. A smaller planet may lose its atmosphere more easily. A more active star may strip away outer layers more efficiently. A different mineral composition may produce different kinds of vapor and dust when heated. For that reason, when the dust tail of a disintegrating planet passes across starlight, it is not telling the story of that world alone. It reminds us that every rocky planet exists because many conditions happen to remain in balance, at least for a time. This idea becomes especially important when humanity searches for potentially habitable worlds. For many years, the concept of a habitable zone was often described in terms of distance, the region where a planet might receive enough energy for liquid water to exist on its surface, assuming the right atmosphere. But distance is only part of the story. A planet located in a favorable region still needs sufficient mass to retain an atmosphere. It needs an appropriate composition. It requires a stellar history that is not excessively destructive. It must follow an evolutionary path that does not strip away critical layers too early. Disintegrating planets lie far beyond that calm and favorable realm, yet precisely because of that, they highlight the conditions necessary for a rocky world to avoid becoming overly exposed and vulnerable. When dust from an ultra-hot planet reveals traces of minerals, it also encourages us to think about the materials from which rocky worlds throughout the galaxy are built. Rocky planets are not necessarily copies of Earth. Some may contain more iron. Others may be poorer in volatile materials. Their crusts may differ. Their mineral ratios may vary, and they may have formed within protoplanetary disks of very different compositions. If a dust tail carries information about surface material, It can help test ideas about this diversity. A faint stream of dust surrounding a planet that is gradually losing itself may become a small but valuable piece of evidence in a much larger question. How different are the rocky worlds scattered throughout our galaxy? Here, the beauty of science emerges from the connection between the very small and the very vast. A dust grain within a planetary tail may be far too small to imagine clearly with the naked eye. Yet if that grain carries the signature of a particular mineral, it becomes linked to the history of planetary formation, to the temperatures within the disk surrounding a young star, and to the creation of heavy elements within generations of stars that existed long before. Rock on a distant planet does not appear from nothing. It is assembled from matter that once passed through stars, stellar explosions, and clouds of gas and dust before gathering into a new planetary system. When a grain of dust leaves a disintegrating planet, it carries not only the memory of a recent surface, but also a connection to a far older history of cosmic matter. This perspective softens the idea of loss as well. An evaporating planet sounds like a story of ending, yet its material does not vanish from the universe. Dust grains pulled away from the surface may disperse, be heated further, fall into the host star, or drift into other orbits around it. They are no longer part of the planet in its original form, but they remain matter nonetheless. The universe does not erase them in any absolute sense. It transforms them, moving them into different states and different locations. A world gradually loses its former shape while its material continues participating in the environment around its star. On cosmic scales, disappearance is often another form of transformation. Seen from Earth, this realization can evoke a curious feeling. We live on a rocky planet that was also built from ancient matter, beneath an atmosphere preserved through gravity, magnetic protection, a favorable distance from the sun, and a long history shaped by fortunate circumstances. Beneath our feet, rock feels steady. Above us, the air feels so natural that it seems as though it has always been there. Yet when we look toward these intensely heated worlds, we realize that such stability is not automatic. It is the result of a delicate balance among many conditions. A planet that retains its surface, atmosphere, and water for long periods of time exists because many different factors happen to work together. In that sense, disintegrating planets do not diminish the beauty of Earth. They make it easier to see. They need not be described as failed versions of rocky worlds. They are simply different possibilities for planetary matter living under different circumstances. In some places, rock cools into continents. In others, it lies beneath a dense and scorching atmosphere. Elsewhere, it dries beneath a thin sky. And in some systems, rock becomes so intensely heated that it turns into vapor and eventually dust within the light of a star. Each possibility is a different answer given by matter to the combined influences of light, gravity, and time. Within the dust trail of a world gradually wearing away, we learn something that is both scientific and quietly profound. Planets are not merely places, they are processes. They form, cool, retain or lose atmospheres, reshape their surfaces, interact with their stars, and sometimes surrender their own material grain by grain. Some of these changes unfold too slowly for a human lifetime to notice. Others, like a dust tail crossing starlight, leave signals clear enough for telescopes to detect. Through them, a disappearing planet tells more than the story of its own fate. It helps us understand, on a broader scale, what it means for a rocky world to exist in the universe. Even though the dust tail of a disintegrating planet can reveal an extraordinary amount of information, it is not a complete answer. It is more like a thin page held against the light, where a few lines, a few shadows, and a few faint patterns become visible enough to know that a larger story exists behind them, but not enough to read every sentence. In exoplanet science, this uncertainty is not a failure. It is the natural state of studying worlds that are so distant, so small, and so close to the overwhelming brightness of their stars. Every signal that reaches us has traveled a long journey. Along the way, it has become mixed with starlight, instrument noise, the natural variability of the star system itself, and the limitations of the models humans use to interpret it. One of the greatest challenges is determining exactly what the tail is made of. When dust dims starlight in a particular way, scientists compare that signal with many possible materials. Some models may fit silicate-rich dust. Others may require particles with different sizes, compositions, or temperatures. Yet the light passing through such a tenuous dust cloud is not always strong enough to separate every possibility with certainty. Two different kinds of dust can sometimes produce remarkably similar signatures if their particle sizes, densities, and distributions are adjusted in certain ways. As a result, what we often obtain is not a definitive list of minerals, but a range of possibilities in which some explanations appear more likely than others. Part of that uncertainty comes from the dust tail itself. It is not a stable object that can be observed repeatedly in exactly the same state. One day there may be more dust, another day less. A particularly hot region of the surface might release material more efficiently for a time. Activity from the host star could sweep the tail away more quickly or destroy dust grains before they survive long enough to leave a stronger signal. If observations capture only a handful of transits, they may reveal only a narrow glimpse of the process. A planet losing mass is not like a rock sitting in a laboratory, where conditions can be carefully controlled. It is more like a small flame burning outdoors, where the smoke changes with the wind, the fuel, the temperature, and the passing moment. There are also questions about the orbital history of these worlds. A planet orbiting extremely close to its star may have formed near its current location, within the hotter inner regions of the system where building materials were scarce and temperatures were high. But it may also have formed farther away and gradually migrated inward through complex gravitational interactions. Planets can tug on one another, orbits can evolve, tidal forces can slowly shrink a planet's path over time. If a world once existed farther from its star, its history could be very different from that of a planet born in the intense heat of the inner system. It may have retained more material, experienced milder conditions, and only later been drawn into a harsher environment. The dust tail we observe today reveals the present state of the world, while much of its deeper past remains hidden within the uncertainties of our models. The planet's original mass is another difficult question. A small object shedding dust today may always have been small, or it may represent the surviving core of a much larger world. Some close-in planets lose thick outer layers of gas, exposing denser interiors beneath. Others gradually erode over immense spans of time, becoming lighter and smaller. In some cases, the object we see disintegrating today may bear little resemblance to its original form. It is the product of a long history during which entire layers may have vanished before humanity ever detected the system. Observing the dust tail now is a little like seeing a tree at the end of autumn without knowing exactly what its first spring looked like. The host star itself introduces additional challenges. A star is not a perfect light bulb. Its surface may contain dark spots, bright regions, flares, pulsations, and many other forms of activity. These subtle variations can complicate the light curve. If a star spot rotates into view at the same time a planet transits, the signal may become distorted. If the star is highly active, the environment surrounding the planet can change as well. Scientists must separate the planet's signal from the star's own behavior, much like trying to hear faint footsteps in a room, while the wind outside is constantly moving the curtains. As telescopes become more advanced, the picture grows clearer, but the limitations never disappear entirely. Instruments can measure starlight with astonishing precision, yet the signal from a small rocky planet remains incredibly faint compared to the brilliance of its host star. Observing at multiple wavelengths helps distinguish between competing explanations, but observing time is precious, and every target must be chosen carefully. A few transits may not reveal the full range of variability. More observations can sharpen the picture, but physical models are still needed to connect the scattered pieces of data. In science, better tools do not replace caution. They simply allow us to ask more subtle questions. This is what makes disintegrating planets such fascinating objects. They are both revealing and elusive. Revealing because their dust tails expose material that most rocky exoplanets keep hidden. Elusive because everything we learn still comes through indirect light, models, and probabilities. We may say that a planet is likely losing dust. We may infer that the dust is consistent with certain minerals. We may estimate a range for the rate of mass loss. Yet between those answers, there is always empty space. That space does not weaken the story. It keeps it alive, open, and waiting for future observations. In the quiet mood of this journey, it is possible to let that uncertainty remain without rushing to fill it. A dust tail passes across starlight. It dims the light. It hints at heated rock, escaping material, and a world orbiting too close to its star. Yet it does not reveal everything. It does not show us every layer beneath the surface. It does not tell the complete history of the orbit. It does not reveal exactly when the process of disintegration began, nor how long it will continue. It simply opens a narrow doorway, and through that doorway humanity sees enough to know that much more lies beyond. That sense of humility feels perfectly suited to astronomy. Looking into the universe is not always about receiving immediate answers. More often, it is about learning to live with small clues, a slightly asymmetric light curve, a faint absorption feature, at a particular wavelength, one transit that differs from the last, a dust tail, visible only through the absence of light. From those subtle signs, scientists construct the best picture possible, always prepared to revise it when new data arrive. The universe does not hand us a complete map. It offers scattered pieces, and the patient work of fitting those pieces together is part of what makes science beautiful. Perhaps the dust tail is most beautiful not because it answers every question, but because it shows that a distant planet can still surprise us. What first appears to be a small, overheated world gradually losing itself becomes something richer, a source of new questions. What is the rock like there? How has the surface changed over time? What stages has the orbit passed through? How long has the star been eroding the planet? And how many similar worlds remain hidden within light curves that have not yet been fully understood? If held gently, those questions do not make the journey heavier. They simply make the dust tail deeper, transforming it from a faint streak in space into a path that extends into the unknown edges of human understanding. A disintegrating planet does not disappear in the way our imagination often suggests. It does not require a final explosion, a colossal fracture splitting its surface in two, or a single dramatic moment that separates a clear before and after. Its disappearance may unfold far more slowly, through countless orbits close to its star. Each time it passes through that intense region of light, the surface absorbs more heat, more mineral vapor rises. Another thin layer of dust is released into space and drawn into the faint tail trailing behind it. If you watched for a day, the planet would still be there. If you watched for a human lifetime, it might still be there. Yet on the vast time scales of the universe, those tiny losses accumulate into a profound transformation. There is a particular quietness in that image. A small rocky world continues circling its star, following the orbit that keeps it within such a harsh environment. It does not resist the star, nor does it leave by choice. It simply exists within a balance that is no longer gentle, enough gravity to remain a planet, but not enough to hold on to every particle heated from its surface, enough mass to continue orbiting its star, yet close enough that heat and radiation constantly challenge its outer layers. Its boundaries therefore become less defined. Part of the world remains within the surviving rock. Another part drifts behind it as dust. If we could view it from afar, not through data, but through imagination, it might appear as a dark point near the brilliant edge of its star. One hemisphere would glow under intense illumination, streaked with orange-red fissures like embers beneath a dark crust. Behind it would stretch a long, thin, gently curving trail of dust, fading into the darkness of space. Yet the beauty of that image does not come from violence. It comes from fragility. The tail is not a great flame. It is material so fine that it is almost invisible, revealed only when it crosses starlight. It is the portion of the planet that has left the surface, but has not yet completely blended into the wider environment of the star system. For a brief time, that dust remains close enough to its origin for us to recognize that it still belongs to the world slowly wearing away. That gradual thinning softens the very idea of what a planet is. In everyday life, we tend to imagine worlds with clear boundaries: rock below, sky above, space beyond. But in extreme environments, those boundaries can become transition zones. Surface rock becomes vapor. Vapor cools into dust. Dust stretches into a tail. The tail disperses and eventually fades into the surrounding light. There is no single line marking where the planet ends. Part of it remains within the rocky core. Part of it is in the process of leaving. Part of it has traveled too far ever to return. A disintegrating planet is therefore not merely an object. It is a process unfolding in space. Within that process, the star serves as both the source of energy and the backdrop for observation. Its light heats the surface, pushes the dust, and sends tiny particles onto different paths. Yet that same light passes through the dust tail and carries information back toward our telescopes. Without the star, the planet might not lose material in this way. Without the star, we might never see the escaping material at all. There is a quiet paradox in this relationship. The very thing making the world thinner is also the thing allowing humanity to know that it is becoming thinner. From far away, telescopes do not witness the entire scene. They simply measure a slight dimming of starlight and then its return. They record transits that are sometimes deeper, sometimes shallower. They detect shadows that are not perfectly round, not perfectly regular, and not quite the same as before. From those subtle changes, we build a story of dust, heat, gravity, and vaporized rock. It is not a perfect story, but it is enough to transform a small signal into a world with character and form. That planet becomes more than a number in a catalog. It gains a heated surface, escaping material, a dusty tail, and a history that continues to evolve with every orbit. What remains after all of this is not a sense of catastrophe, but a sense of time. The universe does not change only through dramatic events. It also changes through processes so gradual that they are almost impossible to notice in a single moment. A star burns its fuel over billions of years. A planet cools over immense stretches of time. An atmosphere may be stripped away layer by layer. A rocky surface may lose material through countless revolutions around its star. Small changes, repeated long enough, can rewrite the fate of an entire world. For us, recognizing that can bring a strange kind of peace. We do not need to stand beside that planet. We do not need to see every grain of dust. We only need to know that light has carried part of its story here across an immense distance, allowing a slowly fading world to be recognized within the quiet language of data. Those dust grains may have vanished long before their signal reached us. The planet itself may continue orbiting its star for ages after the observation was made. Astronomy always carries this gentle mismatch in time. We witness moments that have already left their place of origin, yet those moments remain real enough to deepen our understanding. A planet evaporating before its star is therefore not merely an image of disappearance. It is an image of matter changing form, of light becoming language, of rock leaving memories within dust. It shows us that rocky planets are not motionless spheres, but worlds engaged in a continual relationship with their stars. In some systems, that relationship is gentle enough for surfaces to cool, atmospheres to survive, and water to remain. In others, it is too close, too hot, causing the very substance of the planet to begin drifting away. Both belong to the same universe, where the fate of a world is written by distance, mass, light, and time. And when the dust tail finally drifts across the starlight in our imagination, it leaves behind a remarkably soft echo. A world may be disappearing, yet in the process it continues to give something back. It teaches us that rock can become vapor, that dust can carry memory, and that a tiny shadow crossing a star can reveal the story of an entire planet. Somewhere within the galaxy, that world continues along its orbit, becoming just a little thinner with every revolution, each dusty tail slowly dissolving into the light. And from far away, humanity continues listening to that transformation not through sound, but through the light that is no longer there. When we began this journey, we saw only an unusual shadow passing across the light of a distant star. From that tiny clue emerged a larger picture of worlds orbiting too close to their sources of light, where rock can become so hot that it no longer remains in its familiar state, and where material escapes the surface to form thin, comet-like tails of dust. Layer by layer, the observations revealed more than a rare phenomenon. They offered a different way of seeing rocky planets throughout the universe. These worlds are not motionless spheres that remain unchanged forever. They evolve, interact with their stars, lose or retain material, and follow paths shaped by conditions that determine their destinies long before we ever discovered them. Somewhere out there, these ultra-hot planets continue circling their stars. Some may still be leaving behind faint trails of dust. Some may have been losing material for millions of years. Others may be at the very beginning of the process, with tails still too subtle for current observations to detect. Meanwhile, light continues leaving those distant systems, crossing the vast emptiness between the stars, and carrying tiny variations that only the most sensitive telescopes can recognize. From those almost imperceptible changes, humanity continues assembling a picture of worlds no one has ever visited. Perhaps the most memorable part is not that a planet is losing material. Perhaps it is the way we know. Not through interstellar travel, not through close-up photographs, but through a small amount of missing light as a planet and its dust tail pass in front of a star. A slight dimming became a story about rock, heat, dust, gravity, and time. It reminds us that some of the greatest discoveries in science do not begin with the strongest signals. They begin with subtle differences, just enough to make someone pause and look a little longer. And as we bring this journey to a close, those worlds continue moving. Dust is still being created and dispersed. Light is still leaving distant stars on its way toward the telescopes of the future. Particles that once belonged to a planet continue their own journeys through space. And somewhere within light curves that have not yet been fully explored, there may still be other tales, other worlds, and other stories of rock dissolving into starlight that humanity has only begun to recognize. Thank you for joining this journey tonight. And now, as those distant planets continue their quiet revolutions around their stars and tiny grains of dust drift through the light, perhaps it is time for your own thoughts to slow a little as well. Let the vastness beyond continue moving at its own pace, while you settle gently into the stillness of the night, carrying with you one final image, a world gradually thinning within starlight, yet leaving behind a trace just bright enough to tell its story.